Hi, everyone. As John said, my name is Joe O'Sullivan, and this is my thesis analyzing the potential for wildlife crossing structures along I-5. So this thesis was done with the Washington State Department of Transportation as part of their ongoing I-5 habitat connectivity project. I-5 has created a nearly impassable barrier to wildlife movement from the Southern Cascades area over to the Olympics and Willapa Hills area. There's also a risk for wildlife vehicle collisions along I-5. So throughout the course of multiple studies over the past 10 years, two linkage zones have been identified as choke points where lots of animals come into contact with the interstate from both sides. First is the northern linkage zone, or NLZ, which runs from the southern end of Tumwater down to the Grand Mound area. The second is the southern linkage zone, or SLZ, which runs from the Toledo area down to the city of Castle Rock. 8 new wildlife crossing structures have been proposed between these two linkage zones to address these issues. 3 new overcrossings in the NLZ and 1 overcrossing and 4 new undercrossings in the SLZ. These linkage zones have been monitored over the past 5 years by trail cameras, and the wildlife detections from these cameras is the main data source for this project. The other data source for this project comes from the I-90 Snoqualmie Pass East project. WashDOT has completed 11 wildlife crossing structures on the east side of the pass over I-90, and over 3,000 recorded crossings have occurred since construction on these structures. These structures have also significantly decreased wildlife vehicle collisions in the area, particularly amongst elk. This data will be used to generate an expected use metric for the I-5 structures by taking the recorded I-90 crossings and comparing them to the I-5 detection data around each proposed structure site. This study focused on large and medium mammals that are present both in the I-5 and I-90 areas. These animals are black-tailed deer, coyote, American beaver, elk, American black bear, and cougar. So my research question: how could wildlife crossing structures best be used to increase habitat connectivity and decrease wildlife vehicle collisions along I-5 in Southwest Washington? I'm trying to answer this question through 2 different objectives. The first is to determine the expected use by each species for each proposed wildlife crossing structure on I-5. The second objective was to create models to show how decision makers could best accomplish a variety of different goals using these wildlife crossing structures. So for this first part, I'm trying to answer the question: what structures would be best at increasing habitat connectivity for each species individually? So to answer this question, I created a 2-mile buffer around each proposed wildlife crossing structure, and then I compared the detections of each species within these buffers using a chi-square test. Standard residuals were then calculated to classify each proposed structure as a good, moderate, or bad site for each species. In the subsequent maps that I'll show you, the left side of the circles here, shown on this green to red scale for good to bad detections, is this detection metric. And then on the other side of the circles, on the right-hand side, is the expected use metric. This metric was calculated using the data from the I-90 wildlife crossing structures, and expected crossing rate was calculated. This crossing rate was calculated by taking the number of crossings at a given structure on I-90 and dividing that by the number of detections of that species at that given structure. So for example, if there were 100 black-tailed deer that were detected at the overcrossing on I-90 and 85 of those deer actually used it to cross the road, then black-tailed deer would have an 85% crossing rate. Separate undercrossing and overcrossing rates were calculated for each species. These crossing rates were then applied to the detections that were discussed in the last slide at the proposed I-5 structures to get an expected crossing value for each structure. This expected crossing value was then converted to an expected use score on a 0 to 10 scale, with the structure for each species that scored a 10 being the structure with the most expected use for that species, and a structure that scored a 0 having no expected use. And this was repeated for each species. So I'll now go through each species individually starting with the species with the most detections and going to the one with the least detections. So black-tailed deer, unsurprisingly, are the most commonly detected species along I-5 in the study area. As you can see here, this milepost 90.5 overcrossing had the most expected use of any structure on I-5. But what's really important to point out for black-tailed deer is that they are everywhere. Even the structures with the least expected use still, these two northern linkage overcrossings still have the moderate amount of expected use, and any structure that's built will benefit black-tailed deer habitat connectivity. It's not as important which structure is chosen as it would be for any other species. Next most detected species was coyote. Coyotes clearly had more detections in the northern linkage zone than in the southern linkage zone across the board. And therefore, these structures see more expected use. However, it's the same thing as with the black-tailed deer, where coyotes are everywhere. And any structure that's built, even these ones that don't look as great in the southern linkage zone, still would see a high amount of benefit for habitat connectivity for coyotes. So beaver is where it starts to get a little bit more interesting. The two structures that would see the most expected use for beaver are these two southernmost undercrossings in the southern linkage zone. Another thing to point out for beavers is this milepost 96.1 overcrossing up in the NLZ. As you can see on the left of the circle, there is a high amount of detections in this area, but because it's an overcrossing and beavers are very unlikely to use overcrossings because they're so stream dependent. So because it's an overcrossing, there's no expected use in this area. However, WashDOT is currently in the process of removing a fish barrier here where the star is by Maytown, which and the resulting undercrossing would allow for beavers to pass through. So beaver connectivity is actually already being addressed by WashDOT through separate projects, and it was just not included in this study, but that's pretty exciting. Next, we looked at elk, and elk also saw the most expected use at this milepost 90.5 overcrossing in the NLZ. And then there's a moderate amount of expected use at any of these other four structures scattered throughout the study area. So there are a variety of different options that would likely, at least in some way, benefit elk habitat connectivity. Black bears saw the most expected use at this milepost 92.8 overcrossing in the NLZ, which is interesting because black bears actually have a very strong preference for undercrossings. However, the number of detections was so much higher at this one location that the overcrossing still would see the most expected use, even with black bear's general aversion to overcrossings. The other locations that would likely benefit black bear usage and see high expected use are these two undercrossings in the southern linkage zone, which have less detections, but again, because they're undercrossings, black bears would be more ready to use them. Finally, we'll look at cougars, the rarest species in this study. Cougars, if you look on the left side of the circles, there was no significant difference determined in the number of detections between any site that actually had detections of cougars. Because cougars, like black bears, have a very strong preference for undercrossings, these two southernmost undercrossings in the SLZ scored the best for their expected use for cougars. So they would benefit cougar habitat connectivity the most. So that's a lot of different numbers, and obviously with limited resources, WashDOT isn't going to be able to build an individual structure for each species. So how can decision makers use information to determine which proposed structures would best accomplish all of their goals kind of wrapped up into one if you can only build one or two structures? So here I have example models. These models are not meant to be taken as the exact best solution, but are meant to provide an example of how different values from decision makers can result in different solutions being proposed. So this first model on the right, on the left, is the equal weight connectivity model where each species looked at here is valued equally. Their expected crossing scores are all weighted the same. The second model prefers species with high populations, so black-tailed deer and coyote are weighted the heaviest. This third model shows species with high conservation concern valued the heaviest. So basically the inverse of the previous model, where cougar are weighted by far the heaviest, followed by black bear, then elk and beaver. So the main takeaway from this slide is that there is a lot of variability between these models. Each model shows different structures that would be the most beneficial. However, there are a couple patterns that emerge, which is interesting. These bottom two undercrossings, which are the two southernmost undercrossings in the SLZ, score pretty well across the board. Like if there was one winner to be picked, it would probably be the milepost 53.9 undercrossing. This is also interesting and exciting because these two undercrossings have been identified as the Cowlitz by the Cowlitz tribe, who are one of the partner groups on this project, as priority sites for them because they also are fish barriers to salmon movement. So if these structures were built, it would not only likely greatly benefit wildlife movement, but also help with fish passage in the area. And then if there's a worse structure to be picked, it would be the milepost 58.6 undercrossing, which scores pretty poorly for habitat connectivity across the board. Finally, I'd like to show one last model, which takes the third connectivity model, the one that values cougars the most, and combines that with collision reduction potential and cost effectiveness. This model shows, like the previous one, that the two southernmost undercrossings in the SLZ score pretty well. In this case, the milepost 53.07 actually scores the highest, but both of those still score well. And what's really interesting about this model is that this milepost 58.6 undercrossing, that if you remember scored by far the worst in the previous slide, actually now scores second best because it's in an area where there are a lot of wildlife vehicle collisions, mostly with black-tailed deer, and it's also the cheapest of any of these structures. So again, this just goes to show how different values by decision makers can really drastically change what the best solution for this project would be. So a lot of further research is necessary before anything gets built here. First and foremost, continued monitoring focused on these proposed structure sites is necessary to make sure that the most robust population data can be obtained so decision makers can be as informed as possible when making these decisions. And then fine tuning of these models that I've showed is also necessary because these are just meant to be examples and it will be up to WashDOT and their other partner groups to determine what species they want to focus most on, if they want to include things like collision reduction potential or cost or any other metrics. And then if any structures are actually built, post-construction monitoring will be necessary to determine the success of these methods and answering the question how the expected use that I determined in this study compares to actual use on these structures. I'd like to thank WashDOT's Environmental Services Office for allowing me to work on this project with them, specifically Glenn Kalis and Mr. Pushy, as well as all of the MES faculty for their support throughout this entire project, specifically John, my reader. Thank you.